3.3 practice answers. School newspaper is planning an article on family-friendly places to stay over spring break in a nearby beach town. Editors intend to call 4 randomly chosen hotels and ask about what's going on with them. They have an alphabetized list of 28 hotels. They have 28, and they want to choose 4 using papers of slip. Okay, once again, we have to do the label. Okay, if you remember back in the notes we took, you want to label, then randomize, and then select. Okay, so using slips of paper, so using identical slips of paper. Identical means they're all the same. It means they're all going to have the same probability. Label each hotel on each of 28 papers. Okay, so there's 28 papers, one hotel name on each of those. Okay, we're going to put into a box. We're going to mix the papers. Okay, so that's the randomizing part. So the labeling, the randomizing, and lastly, the choosing. Select, we want 4, right? 4 pieces of paper. Call those hotels. Okay, so that's part A. Part B, same thing using a random number generator. Okay, we can alphabetize the hotels, label each hotel number 1 through 28. Okay, so there we labeled them. Use a random number generator, like we did on random.org, to select 4 unique numbers, and then the 4 numbers correspond to the hotel is then surveyed. Okay. Next one, number 2 for you guys. So, Genealogical Society in Illinois has compiled records of that many gravestones and cemeteries in the county for years there to there. Historians plan to use these records to learn more about African Americans and their history. They choose a simple random sample of 395 records to check their accuracy by visiting the actual gravestones. Okay, so there are a total, our population, you don't have to write this, the population was 55,914, and we're collecting a sample of 395 gravestones to visit. Okay, why would it be difficult to select a simple random sample of that many gravestones using slips of paper? It would be hard to order. Hard to label and order the gravestones. Okay, it could be done, but think about there's this many gravestones. If you want to put those in order, it'd be kind of hard to do that. Well, not only is it hard to order, but there's maybe more specific. There are almost 50. There's 55,914 slips of paper. That's a lot to do. That might be an even better answer. Using slips of paper, it'd be hard to do. Okay, because there's that many. How to do a simple random sample? Okay, once again, we're going to label. So label each gravestone. Sorry, you couldn't see it. So label each gravestone numbers 1 through 55,914. Use a random number generator, like random.org, to select 395 unique numbers. And then the selection, select the gravestone with that number to survey. Okay, so you have the labeling, the randomizing, the selecting. Okay. Okay, next problem. Estimating a mean. In a simple random sample of 100 calls to a customer service line, the mean time a caller is placed on hold was 12.5 minutes. Being put on hold when you try and call somebody, okay? But average person was 12.5 minutes. In a call of 100 calls, the average was 12.5. Do you think the mean time that all callers in the customer service line was placed on a 12.5? So we collected a sample of 100, and the mean was 12.5 minutes. Do you think the actual population mean is also 12.5? Probably not. A sample is maybe close to, but probably not exactly. The same as the population. The same as the population. Okay, when I collect a sample, the sample is 12.5 minutes. The population, right, of everyone might be 12.5 minutes. It might be close to that. It might not be, though, too. There's some variation in that. Okay, suppose the customer service manager had only time to collect 25 calls before reporting. What effect would this have on the mean? Okay, so if you remember, if we had, say this is our true mean, right? That 12.5, when we had a sample of 1,000, it's probably somewhere, around there, right? If I take less people, it's going to be more spread out. So it's going to be more spread from the true population mean. Okay, does that make sense? So our sample, if this is our true one, right? Our sample, if I'm selecting a sample of 100, it's probably going to be somewhere close to that. But if a sample is down to 25, it's going to be less accurate. So it could be all over the place. Okay. Number 4, during the political crisis in Ukraine in 2014, a national poll organization asked a simple random sample of 2,066 Americans to locate Ukraine on a map. The proportion who successfully located Ukraine was over 16, almost 17%. That's very low. We should know our maps a little bit better here in the U.S. But anyway, part A. Do you think that the population of all Americans who can locate Ukraine is actually 16.6%? Probably not. And the same is up there. A sample could be close, but most likely not exact. Okay, so now let's say instead of 2,066 Americans, let's only survey 500 Americans. So it'll be more spread out. Okay, so which is most likely farther from the true mean, or in this case, proportion. Okay, so the true proportion of all US is some number, right? If I get a big sample, like over 2,000, that's probably getting somewhat close to here. But if I take a less of a sample, most likely it's more spread out and farther away from the true proportion. Okay. Okay. When a coin is flipped, we all know the probability that it's going to be in heads is 50%, 50-50. What if you spun a coin, though? Okay, 2 Polish math professors and their students spun this coin 250 times, and it landed heads 140 times. One of the professors concluded that the coin was minted asymmetrically and more likely to land on heads. Now, is that really true? Okay, so maybe it could have just happened by chance, right? Maybe it really is 50-50, but you just got a little bit more than 50% just by chance. So to determine if this data was convincing evidence, they did 100 trials of the simulation. So they had spun it 250 times. They did it 250 times, 100 times. So this is 250 times, that's 250 times, that's 250 times, and they calculated how many heads there were. Okay? Now, most of the time, if it really is 50-50, if I spin it 250 times, I would get 125 heads, most likely, right? If it's 50-50. So you can see it's somewhat close to that. I'm not sure about that gap there. That's kind of interesting. But anyway, we would expect it to be somewhere around this area here, which most of our data is. We would, by chance, have sometimes more heads or less heads, but we would expect it to be around here at 50%. Now, they got 140. So the probability of it being over 140 is 3 out of the 100. Okay? Which is very unlikely. So it probably means that it is unbalanced. It's not 50-50. Okay? So part A, variability. If the number is 50-50, we would expect out of 200 spins to have around 125 heads. Okay? But by chance, we might have a few more or less. Than the 150. Okay? So we would expect 150, but just by chance, when we flip it, right, when we spin a coin, we're gonna be, around 50%, but probably more or less a lot of the times. Okay? So part B, based on this simulation, is there convincing evidence that the coin is more likely to land on heads? So we had 150, yeah, so 3 out of the 100, which is only 3% of the time, did they get 140 or greater. Therefore, it's not likely to happen by chance. Okay? Not likely to happen by chance, therefore probably not a 50-50 coin. Okay? Probably not 50-50 because it wouldn't just happen by chance. Okay? Kissing the right way. Hopefully you don't go around kissing people, but if you would, do you kiss to the right, lean your head to the right or to the left? Okay? So according to a newspaper article, most people are kissing the right way. That is, according to the study, the majority of couples prefer to tilt their head to the right when kissing. In the study, a researcher observed a random sample of 124 kissing couples and found that 83, which is about 60, almost 67%, of the couples tilted to the right. To determine if this data provided convincing evidence that the couples were more likely to tilt their heads to the right, they did this simulation 100 times. Each dot shows the number of couples that tilt their head to this in a simulation of 124 couples, assuming that it's 50% of the time. So if it's 124 couples, and let's assume they don't have a preference one way or the other, it would be 50-50. So we would expect 62 to lean one way and 62 to lean the other way. So tilting to the right, we would expect to have around 62. Now, we would expect some, just because we're doing a survey, some variation. Okay, some right around 62, but some right, some below, and some above. So that's part A. We would expect 62, but we do have some variation just based upon sampling. So part B, I'll write that down. We would expect 62 out of 124 to tilt right if they had no preference. Okay, but with some variation. Above and below 62. Okay, part B. Now, in this, it was 83 out of it, right? So 83. Did we have any couple, like if it was 50-50, was there any sample that had 83 or above? No. Okay, there was none of them that were 83 and above, which means it's probably not 50-50. It probably, people do prefer to go to the right. There were no simulations 83 or above. Therefore, 83 does not happen by chance very often. Therefore, it kind of proves couples prefer to tilt right when kissing. Okay. And our last problem. A college administrator wants to estimate the mean distance that students at a large college live from campus. To find out, she obtains a list of all the students that go to the school. How would you select a simple random sample of 100 students? Okay, now you can use the slips of paper or random number generator. Remember, label each student with a number one to the end. It doesn't tell us how many students there are, it just says large. So we'll just number them 1 to the end. Okay, label them. We will use a random number generator, like random.org, to select 100 unique numbers. The people corresponding to those numbers are selected to survey. Okay, label, and then mix them up, or randomize it, and then assign them. Okay, part B, will your sample results be exactly the same as the true population? So in other words, will these 100 people be exactly the same as the whole population? No. The sample will vary a bit from the population. Okay, we hope the sample is going to be close to what the population is, but it's not going to be exactly the same. C, which would be more likely to yield a sample closer to the true population proportion? Okay, bigger samples, which in this case the bigger one is 100, would most likely be closer to the true population mean. Okay, bigger samples are more accurate.